receiving Peter Humphries from University College London. Will talk to us about the random wave conjecture and arithmetic quantum chaos. So Peter, the floor is yours.
Okay, so the invitation, the introduction. My internet isn't great, so let me know in the chat. I have the chat open, so let me know if the chat if it's lagging too much. I can always try turning off my video, and then it'll probably survive. So everything I want to talk about today is kind of number theoretic, but I want to try and hide the number theory as much as possible and make it much more spectral. So the goal is to talk about quantum chaos, in particular about refinements of quantum unique ergodicity. So I'll start by kind of mentioning the relation between classical chaos and quantum chaos. So the idea is basically to understand how classical mechanics and quantum mechanics are related to S limits. So here's the mathematical formulation I want to start with. We start with a surface M, so some two-dimensional Riemannian manifold. We'll assume that it's compact. And in this case, the state of motions that we're interested in is tuples of a position on that manifold and a momentum. So momentum lies on, you can think of this as lying on the cotangent space. And phase space is the set of all possible states of motion. So positions plus momenta, which you can just think of as the unit cotangent bundle. And the dynamics of these motions, of these states of motions, can be thought of as just the motion over time by Newton's laws, which in this case you can think of as via the geodesic flow. So you start with a point and a direction. The geodesic flow tells you how this position will transform over time. This is dynamics classical dynamics on a surface. What I'm more interested in is the quantum mechanics, which is instead of working with these continuous things, we work with discrete things. So here we work with wave functions, which you can think of as a function on the manifold, as well as being a function of time. So it takes position and time. And instead of working with geodesic dynamics, we work with Schrödinger dynamics. So we have these motions, which we can think of as being determined by what the probability of a particle will be at time t in a region B. And this is completely determined in terms of this integration here, this L2 integration. Now states are just basically L2 space on this manifold. And the dynamics, instead of being geodesic flow, the Schrödinger equation. And what's particularly nice about these states is that you can choose states that don't depend on time. Or rather, you can expand your wave function as an infinite sum over wave functions that are independent of time. They're known as stationary states. So you can think of these as ones which the probability density is independent of time. So this is just a function of space times some function of space and time, but this has absolute value 1. And because these states are solutions to the Schrödinger equation, when we separate variables in this way, we find out that these stationary states correspond to solutions of an eigenvalue problem. So Laplacian of phi plus an eigenvalue times phi is equal to 0. So here I'm normalizing this so that the eigenvalues, I want these to be non-negative. So eigenvalues should be non-negative. And I'm only interested right now in manifolds that do not have any boundary, although obviously you can set this up completely with boundary and everything works. So as I'm sure essentially everyone here knows, is that these Laplacian eigenfunctions have very nice properties. For example, if you're on a compact Riemannian manifold, and we look at the set of solutions to this eigenvalue problem, then the spectrum is discrete. It's non-negative. The spectrum converges to tends off to infinity. And the space of these eigenfunctions, these eigenfunctions form an orthonormal basis, once you suitably normalize them, of L2 of M. So these are particularly nice in that they completely give a basis of this space. And I'll use this fact a fair bit, that these eigenfunctions form a basis of an L2 basis of this space. So one of the fundamental notions of quantum chaos is that this classical model of classical motion and classical dynamics should somehow appear as a limiting behavior of the quantum model. So we should expect that if quantum dynamics behave in some way, then classical dynamics also behave in some way, which is kind of a very wishy-washy way of saying things. And so we have various ways to make this precise. So what you can think of this as saying is that Laplacian eigenfunctions, their limiting behavior as the eigenvalue tends to infinity, as we look at increasing energy levels, this should somehow reflect various properties of the geodesic flow. So I think the first time this was stated in any sense is due to Sir Michael Berry in the late 70s. And one formulation of this statement is that if the geodesic flow on the unit cotangent bundle is ergodic, which I'll explain shortly, then Laplacian eigenfunctions should behave randomly in a large eigenvalue limit. So again, this isn't really well posed. I mean, Berry's a physicist and he did make this at least somewhat more rigorous, but still not a very rigorous statement. So what I'm going to talk about in this talk are various ways of quantifying this notion of ergodic geodesic flow implying a random behavior of Laplacian eigenfunctions. And one can also say things about what this says in terms of Laplacian eigenvalues, which of course is interest to many spectral theorists and certainly also to number theorists. But for this talk, I'm mostly just going to be concentrating on Laplacian eigenfunctions in the high energy limit. So I'm not interested in low energies. I'm just going to be looking at high energies and what these Laplacian eigenfunctions behave like as this energy tends to infinity. So I want to talk about, first about what it means for the geodesic flow to be ergodic, which means I should talk about equidistribution. This is a purely probabilistic notion, although it can be interpreted in terms of weak star convergence, as I'll explain. So I want to kind of set up the general notion of equidistribution in the first place. So we start with any topological space M. We have a limiting probability measure mu on M, and we have some family of probability measures mu t on M indexed by t. So t could be a discrete set or it could be a continuous set. And we say that this family of probability measures mu t equidistributes on M with respect to this limiting measure mu if the mu t measure of every nice set B converges to the mu measure of B. So here nice just means that its boundary has measure 0. And if you use Urson's lemma, you can see this is equivalent to something in terms of nice functions. So we say that this family of probability measures mu t equidistributes on M with respect to the limiting measure mu if the mu t integral of every nice function f converges to the integral of f with respect to the limiting measure mu. So here nice means continuous and bounded. So you can think of this completely in terms of weak star convergence. This is kind of a natural way a functional analyst would think of it. If you're a probabilist, you would call this convergence and distribution. And if you're a probabilist, you might also call this weak convergence, which is a terrible name because it's really weak star, not weak convergence. So what this means in terms of ergodic geodesic flow is the following. We say that a classical system is ergodic if the orbit of almost every point xi in the unit cotangent bundle under the classical dynamics of the geodesic flow is equidistributed in the unit cotangent bundle with respect to the natural probability measure on this, which is the Liouville measure. So we can think of this saying is that if I start with a point in a direction and I let it flow under time by the geodesic flow, then this should spread out uniformly, both in position and momentum on the unit cotangent bundle. So it should kind of cover this space completely uniformly as we spend longer and longer transforming under the geodesic flow. So here's a kind of nice visualization of this. This is the stadium. So we start with a particle here in this direction, and we just let, we act on this by geodesic flow. So here this has boundary, but the case I'm going to talk about later on does not have boundary. So here we go here, we bounce off these walls, we continue over time, and we ask how this looks as we go further and further along in time, and you end up with something that might look something like this. So this seems to be covering the stadium pretty uniformly. And also, if we look at this also in terms of directions, so not only looking at how this behaves on the space, but also its lift to the unit cotangent bundle, and also it's covering that uniformly. Now, we said that this system is ergodic if the orbit of almost every point is equidistributed. And that's because we allow for the fact that there might be some bad orbits. So there are certainly some positions and directions we could take where we don't spread out. So if we start here and we go to the right, then we just bounce back and forth. There are also these nice kind of periodic orbits here under the geodesic flow. So these are closed geodesics. And also if you start inside the rectangular part of the stadium and you go straight up or straight down, then you're just going to bounce back and forth forever. And particularly you're going to see that no matter which point you start with inside the rectangle, you're going to get these ones. So there's an infinitely parameterized family of these bouncing ball modes, these geodesics that are closed. But thankfully these have measure 0 in a whole space. So in particular, the geodesic flow on this space, on the stadium, is ergodic. So that's the classical notion of ergodicity. The quantum notion of ergodicity is the following. I'm going to first define unique ergodicity, and then I'll talk about quantum ergodicity as well. So a quantum system is said to be uniquely ergodic if the probability densities, phi j squared, of the stationary states become equidistributed as the Laplacian eigenvalue tends to infinity, as the energy tends to infinity. So you can think of this as saying the L2 mass of any Laplacian eigenfunction on this manifold becomes equidistributed, covers everywhere evenly, gives the same amount of mass to any region of a manifold. So this means that for all nice sets B, the amount of L2 mass of phi j squared in this set B converges to the volume of B once to be normalized. Or it could be anything of this is that phi j squared converges in the weak star topology to the uniform, the normalized uniform volume measure in this space. So now we have this conjecture known as quantum unique ergodicity. I'm going to warn you, the version I'm stating here, first off, isn't the most general version, and secondly, it's false, but I'll correct myself later on. So this is known as quantum unique ergodicity on configuration space. So we take a manifold M, that's a compact Riemann surface, Riemannian manifold, that's a surface, whose geodesic flow is ergodic. Then QUE states that these probability densities phi j squared of the stationary states become equidistributed on the manifold as the Laplacian eigenvalue tends to infinity. So this is quantum unique ergodicity on configuration space. The stronger formulation, which is probably of more interest, is QU on phase space, where we lift these probability measures phi j squared to microlocal lifts on the unit cotangent bundle. Then instead of equidistribution with respect to the volume measure on our manifold, the equidistribution is with respect to the Liouville measure on the unit cotangent bundle. So it turns out this conjecture isn't quite correct when you modify it slightly. So let me first show you what this looks like in various cases. Oh, sorry, let me first explain what quantum ergodicity is. So quantum ergodicity is where we allow for the case of there being some bad Laplacian eigenfunctions, so long as this bad set of Laplacian eigenfunctions is very thin. So instead of asking that these probability measures equidistribute, we allow ourselves to excise a bad subsequence. So instead of needing the full sequence to converge, we just need a subsequence of density 1. So density 1 is just here. It means that basically almost every member of this sequence occurs in their subsequence. So this is a theorem due to Schnirelmann, I guess in the late 70s and in mid 70s, also by Colin de Verdier and Zeldich. So you can think of these as manifestations of a certain random wave model, which again is due to Berry. And what the conjecture is, very, very roughly stated, is that as this Laplacian eigenvalue tends to infinity, Laplacian eigenfunctions on surfaces with chaotic classical dynamics, for example, having ergodic geodesic flow, should be well modeled by random waves. And Berry only really defines what random waves are when he's looking at things on the sphere, but you can kind of think of them in the following way. Basically, you should think of random waves as being a probabilistic model of Laplacian eigenfunctions. So a random wave is essentially a linear combination of Laplacian eigenfunctions. So these Laplacian functions are phi j. We take a subset of them where J is in some parameterizing set, large J. Usually you can think of this as being in some sort of maybe a dyadic window, maybe a smaller window. So some small window of Laplacian eigenfunctions. And we weight these probabilistically. We weight these by independent, identically distributed Gaussian random variables. And then what this means is that instead of studying eigenfunctions deterministically, completely analytically, basically, so because we now have these weightings by Gaussian random variables, you can kind of study what properties of these hold probabilistically in terms of these random weights. So in particular, if you can prove something about these Laplacian eigenfunctions via this random model, then you might hope for it to be true for the Laplacian eigenfunctions itself. This is the notion of a random weight. And there are various ways to quantify this. There are various properties of Laplacian eigenfunctions you can study by this model. And there are also various models, because I haven't actually specified what I mean in terms of the limiting behavior. So you should think of this as saying there are various possible windows I could take, various sets J could take, where these get larger and larger, or they get further off to infinity. So these are kind of the limiting behaviors we want to study. So there's been some quite interesting recent work of Matthew Corsi Island and also of Xiaolong Han and Melissa Tacey studying these random models.
May I ask a question, please?
By all means.
I'm just trying to understand the statement of quantum ergodicity and the quantum unique ergodicity. A relationship between eigenvalues of the Laplacian and lengths of closed geodesics on compact Riemann surfaces. So in some sense, when you're going to, when you're taking the limit as over all eigenvalues, you're looking at geodesics which are longer and longer. And because you mentioned that the geodesic flow is ergodic, it means that in the limit, the geodesic, this really long length geodesic basically covers the entire surface.
I'm not sure what the question is there. Is there?
Yeah, I'm coming to that. So is it because of this fact that the geodesic is covering the entire surface that you expect the probability measure to approach the volume, the measure given by the volume? Or that
it's not exactly that, but it would kind of take me too long to get into. If you want to,
that's okay. I mean, if it's too much off of topic.
Yeah, I suppose that the two-word answer is something known as Egorov's theorem, but that's not a very satisfactory answer.
And the error time included there. That's,
yeah.
I see. And just a general question: the Bunimovich state, is it that doesn't look uniformly ergodic? Although you've never assumed uniform ergodicity, but
it's not uniquely ergodic in the sense that there are some bad positions and momenta for which you don't have ergodicity. Is that what you meant by that, or are you trying to say something more specific?
No, uniformly ergodic. So it seems that these geodesics don't distribute themselves uniformly, which you would expect, let's say, for a rectangular billiard table.
No, they are uniform. Like, if I understand what you mean by uniformly ergodic, you just mean that these are equidistributed, like these.
Right. I mean, I'm just guessing. Look, just from the picture, it seems that they're not very uniform, but maybe you need more iterations over.
Yeah, I mean, if you keep going further and further, this will cover this completely randomly, and we'll spend the correct amount of time in each region. So not only is it dense, which is just kind of a very weak statement, but it's equidistributed. It genuinely covers each area the correct amount of time.
I see. And so, again, in trying to understand the difference between quantum unique ergodicity and quantum ergodicity, the bad measures, how would you, so what is going on there? Is the probability of the particle being in on a submanifold of the Riemann surface is higher?
Yeah, so I'll show you some pictures of this in a second.
Okay, and okay, thank you.
No worries. Any other questions before I continue? Or feel free to ask them in chat at any point if you wish. Okay. So here are some pictures. The first example is something where the geodesic flow is very far from being ergodic. It's completely integrable. This is the torus. And then we have very high multiplicities of eigenvalues of Laplacian. And there's kind of a nice standard basis of eigenfunctions Laplacian on the torus. You can write it down quite explicitly, basically just in terms of sines and cosines. And what you'll see is that with this standard basis, you really don't see much randomness. Like basically, so this is, you can think of this as a density plot of the L2 density of each eigenfunction. And you can see they're kind of concentrating in different areas, but they're not uniformly concentrating. So here, you're really not seeing any randomness at all. On the other hand, if you look at the stadium, then you kind of usually see randomness. So what you see here is that, so these are, this picture is due to Alex Barnett, and here you see a bunch of different L2 density plots of various Laplacian eigenfunctions. I think for these, the square root of the eigenvalue is roughly 500. And what you're seeing is that usually these kind of seem to be spreading out randomly, but there are some cases, for example, here it seems to mostly be concentrated inside the wings, and this Laplacian eigenfunction here is completely, sorry, concentrated away from the wings. And this Laplacian eigenfunction here is basically seems to be completely concentrated inside the rectangular part. It's completely avoiding the wings of this statement. There's a question, what if you take a flat torus with not asymptotic to the square? You still don't see randomness. So because you want the geodesic flow to be ergodic on the unit cotangent bundle, just not the space itself, you're not going to see randomness. On the other hand, you can, because you have high multiplicities of the spectrum, you can choose base for which you do get randomness. So this is kind of a probabilistic way of looking at it. You can choose linear combinations of eigenfunctions, which you do get very random behavior, which is something that Igor Wigman, who's in the audience, would tell you a lot about. And Andrea Sartori, if he's still here.
But maybe a small comment in position, there are some restrictions. If you just look at squares of eigenfunctions, even with linear combinations, there is a limit. Like in 2D, you can only get trigonometric polynomials and things like that.
Yeah.
So in momentum, you do not have ergodicity, but a perfect example of quantum unique ergodicity is a one-dimensional, is a circle, right? Where sine of n times x. So if the frequencies go to infinity, then you get quantum ergodicity in position, but not in moment. Anyway, sorry.
Yeah, thanks, Timo. Okay, so going back to this picture here, as we saw, this Laplacian eigenfunction does not seem to be concentrating uniformly. It seems to be avoiding some regions and giving too much mass to other regions. And so this was rigorously proved by Andrew Hassel about 10 years ago. He showed that for the stadium, although we have quantum ergodicity, which states that a full density subsequence of eigenfunctions equidistribute, there does exist a thin subsequence for which these probability densities scar in certain regions. They concentrate inside this rectangular period. What I've written here isn't quite correct. What he actually shows is that you can parameterize the stadium in terms of the length of the rectangular part, and you can view this as a parameter t, and then he shows that for almost all t, there does exist this bad sequence of eigenfunctions. Anyway, it's really quite beautiful results that kind of can be thought of as a counterexample to QUE, because the geodesic flow here is ergodic, but we do not have quantum unique ergodicity. So you need something stronger than the geodesic flow being ergodic. There are various suggestions. In this setting, the kind of standard conjecture is due to Rudnick and Sarnak, which states that we should have M being a compact Riemannian surface of negative sectional curvature. So negative sectional curvature certainly implies the geodesic flow is ergodic, but it implies much more than this. So the conjecture is that if we impose this condition, then we do indeed have quantum unique ergodicity. In particular, you'll notice that the stadium does not have negative sectional curvature. So this conjecture is kind of one of the major conjectures in large energy limit studies of Laplacian eigenfunctions. And it's essentially completely open except for arithmetic surfaces. There's also some results on toy models such as the quantum cat map. So I want to talk about strengthings of quantum ergodicity. So even though this is a conjecture that looks very difficult and it's only been solved in arithmetic cases, I want to ask what is the true kind of strongest version of quantum ergodicity. And you can think of this as asking how we quantify the rate of equidistribution of these measures mu j, where mu j is the absolute value squared of phi j d volume, with respect to this limiting measure mu d vol. So one way to quantify is to ask about the error term. So equidistribution says that mu j of b converges to the volume of b for every nice set b, which means that this is equal to this plus some error term. And the question is, how small is this error term as a function of j, or as a function of Laplacian eigenvalue? So how quickly does the L2 mass of Laplacian eigenfunction spread out randomly on our manifold? And here you can use the random wave model to give you a heuristic. So if you do this random waves, then you get square root cancellation. And the square root cancellation comes from the Planck scale, which is 1 over the square root of the eigenvalue. So you might hope for 1 over square root of this. So you might hope that this error term is 1 over square root of square root of the eigenvalue. So this leads us to this conjecture, QUE with an optimal rate. So it says that these probability densities phi j squared equidistribute on any nice set, say for a fixed ball, as the eigenvalue tends to infinity, with an error term of size lambda j to the minus a quarter plus epsilon. So we're giving ourselves a little epsilon room. And towards this little is known, if we do this for quantum ergodicity instead of quantum unique ergodicity, then we do have a rate, but it's just 1 over the log of the eigenvalue. So this is due to Steve Zeldich. I think that's the best known. So this is a far cry from what you might hope for. I will say this conjecture might be hopelessly optimistic, but it does seem to be true for in the arithmetic setting, and I'll try to say about that more later on. So a second way of quantifying quantum ergodicity is another way of quantifying this rate of equidistribution. And this is a modification of the problem known as small-scale equidistribution, which you can think of as a shrinking target problem. So we take probability mu j, so phi j squared d volume. We integrate against some nice test function, so say the indicator function of a ball, and we shrink that ball and ask if we still get equidistribution. So if the L2 mass still equidistributes on a target that shrinks as the eigenvalue tends to infinity. So equidistribution tells us that this converges to 1 if the radius of this ball is fixed. And the question is, how quickly can this radius shrink and still get equidistribution? So when we get to, yes, question?
Yeah, so this rate of, this rate that you're computing is a completely quantum quantity. It has no classical analog.
Yeah, I think that's correct.
And okay, is this related to Ehrenfest time in any way?
So Zeldich's result is right, this natural barrier. But in other settings, you might hope to get well past this. I mean, this is an obstacle, but if you believe this random wave model, then you should still get power rates rather than logarithmic rates. But the Ehrenfest time is a logarithmic rate barrier.
That's true, yeah. Okay, thanks.
So you can think of this small-scale equidistribution result as finding out the scale which we zoom into these Laplacian eigenfunctions, which once we zoom in so far, they no longer behave randomly. They no longer have this kind of random wave behavior, and they kind of behave not randomly at all. So you can think of this, another way of saying this is, how small does a ball have to be to not contain the expected amount of L2 mass of a Laplacian eigenfunction? And again, we have a random wave model, which says that we should expect to behave randomly so long as the scale is above the Planck scale. The Planck scale being 1 over the square root of the eigenvalue. So you should expect equidistribution, provided you're equidistributing on a shrinking ball whose radius is a little larger than the Planck scale. So the radius is bigger than eigenvalue to the -1/2, and then we give ourselves a little bit extra. And this is recently we studied by Zhao and Han, and evidently by Hazari and Riviere. They showed that not for quantum unique ergodicity, but for quantum ergodicity, we do have some rates, but unfortunately it's just a very small power of log. So again, this is related to the error in the first time. So we do get some small scale equidistribution rate, but it's far shy of the actual optimal scale. And if you look at this problem for random waves, this has been studied by Matthew de Courcy-Island and Hazari and Riviere and Han and Tacey, and I guess Granville and Wigman, and who else? Rudnick and Lester. So many people have studied this in recent years in more kind of random settings. If you're a problem, you might think about problem in the following way. You can think about defining a random variable as being the mu-j integral of the mu-j measure of a ball of radius rj centered at y divided by the mu measure of the ball of rj centered at y. So this is a function from the manifold to the positive reals. And here rj shrinks at some rate as the eigenvalue tends to infinity. So equidistribution is just the statement that this has expectation 1. Small scale equidistribution is the pointwise convergence of this to 1. And what I'm going to talk about later on in this talk is small scale equidistribution almost everywhere, which is kind of convergence and probability of this random variable to 1. So we look at the set of centers of balls y for which equidistribution fails, which this minus the expectation is unusually large. It's larger than any fixed epsilon. So this is saying that in almost every ball of shrinking radius, we have equidistribution. Okay, and a final kind of quantification of this random wave conjecture I want to mention is the Gaussian moments conjecture. So this says that Laplacian eigenfunctions should have Gaussian random behavior in the large eigenvalue limit. So one more way is to look at this is look at the moments of the Laplacian eigenfunction as the eigenvalue tends to infinity. So you take phi j of x, you take its nth power. Here we should think of this as a real value function just by normalizing the constants appropriately. And the Gaussian moments conjecture says that the integral of phi j of x to the n should converge to the nth moment of a Gaussian random variable. So this basically should vanish if n is odd, and it should converge to this if n is even. So if n is even, this is just the same as the Ln norm of this Laplacian eigenfunction. So this is very closely related to the problem of understanding LP bounds for Laplacian eigenfunctions. But it's asking for something a little bit more, and it's only asking this is a positive integer or a non-negative integer. So in the case of LP bounds, this is a very well-known result of SOG. And if your manifold has negative sectional curvature, then you can do a little bit better, as this recent work of, I think, Hassel and Tacey, and more recently by Jeff Galkowski and Shiza Kanzani. I don't know if either in the audience today. So that's kind of a weaker statement when you're just looking for upper bounds for these LP norms. But if you're actually looking for these moments themselves, we have this very, very strong conjecture, which is that you have this Gaussian behavior. These should behave like this. So obviously this is true if n is equal to 0. If n equals to 1, this is just the inner product of phi j with a constant function. And because they're Laplacian eigenfunctions, this is just 0. So this is obviously true. And if n is equal to 2, this is just the L2 norm of phi j. And because this is L2 normalized, this is equal to 1 and everything is correct. So this result is trivially true if n is 0, 1, or 2, and unknown otherwise. But if m is an arithmetic manifold, which I'll talk about in a second, then we can start to make some progress. So for the rest of the talk, I'll talk about what happens in arithmetic settings and why we can prove stronger result in arithmetic settings. I will try to not use too much arithmetic, too much number theory in actual proof. I'll try to talk more about the spectral ideas.
Peter.
Yes.
Short question. So there is this old example of Rudnick-Sarnak where eigenfunctions on hyperbolic free manifolds get polynomially big at some Higner points, right? And
yes.
so probably that would violate kind of the most optimistic small scale quantum ergodicity if you let the radius of a ball shrink polynomially at a certain rate.
Yeah, so this in fact is a yet to appear in the archive result of Dimitris Harsakos, Nicole Ralph, and Robin Fro.
Oh, okay. So they figured out the exact rate at which it fails too.
Yeah, they show that in these arithmetic three manifolds, you don't even get to the Planck scale. But this is kind of a special situation.
And of course there are higher dimensional things by like Bunimovich and Decay. Yeah. Right? Okay.
Yeah, this is exactly what is you've hit exactly on the nose right there. That is a fascinating result. So yes, this should hopefully appear in the archive at some point soon. The paper's been circulating for a while.
Okay, thanks. Mm-hmm.
Sorry, I just want to understand the question that was just asked. So you're looking at Bianchi manifolds, and there was a statement that eigenfunctions restricted to CM points.
Yeah. So here's the Planck scale QUE conjecture: is that if you shrink on a ball whose radius is slightly larger than the Planck scale, then you should get equidistribution. And there is a result that on Bianchi manifolds, which are arithmetic ones, equidistribution can fail at a scale polynomially larger than that. So you don't get down to the optimal scale, but this is for like highly unusual reasons. Okay, so for the rest of the talk, I'm going to be talking about a specific manifold M. This manifold is non-compact, but it does have finite volume. The fact that it's non-compact adds some interesting difficulties, but it makes the question interesting in some ways. So the manifold is called the modular surface. It's basically a subspace of the upper half plane. So if you think of this being the real axis, the upper half plane is up here, and this is kind of the subset. So this is imaginary part is between -1/2 and 1/2, and also its distance at least 1 from the origin. So there's this semicircle. And this manifold doesn't have boundaries. So this side is identified with this side, and also this half, the bottom side of the circle, is identified with this half. There is a cusp off at infinity, so this is not finite. This is not compact. The geodesic flow looks something like this. So this is what a geodesic might look like over time. In particular, this has negative curvature because it's lying in the upper half plane. The geodesic flow is certainly ergodic. So this is a picture I stole from the website of Konstantin Kogler, who's a student at Zurich. He also has this great picture of this geodesic flow after a longer time, which covers this really quite uniformly. The problem is the picture is 12 megabytes, and when I tried to include this slide, tech wouldn't compile and kept crashing, so I unfortunately couldn't include it. So this is what the geodesic flow looks like, and Laplacian eigenfunctions look something like this. So earlier I showed you Laplacian eigenfunctions for the stadium, and this is what they look like on the modular surface. So here, the square root of Laplacian eigenvalue is again roughly 500. Because we're on the upper half plane, we have a hyperbolic metric. So distance up here is comparable to distance down here. You have to divide through by 1 over y. So this is why it looks like it's concentrated more over here than up here. But in fact, they concentrate at the same rate with respect to the hyperbolic metric. So these are various different Laplacian eigenfunctions. And as you can see, they seem to have pretty random behavior once you account for the hyperbolic metric. So let me tell you what these eigenfunctions are. So you can think of these as functions on the upper half plane, the complex upper half plane, to the complex numbers. These are smooth functions. They're invariant. So the modular surface is H mod gamma. Gamma here is SL2Z. So the space of 2 by 2 matrices with integer entries and determinant 1, which acts in the upper half plane by Mobius transformations. And if you mod out by this action, you get a fundamental domain for this space, H mod gamma, which is just this here. There are various other fundamental domains that you could choose as well. This means you can think of these as functions on the whole space, on the whole upper half plane, that satisfy this invariance property, that if you act by a Mobius transformation, where the Mobius transformation comes from integer entries that have determinant 1, then your Laplacian eigenfunction is invariant by this. So the Laplacian here is y squared d squared dx squared plus d squared dy squared. So this is the hyperbolic Laplacian. And we want this to be an eigenfunction of Laplacian. And we want the eigenvalue to be non-negative. So this has constant negative curvature, this space, which means the geodesic flow is ergodic. It's non-compact, it has a cusp off infinity, but it's finite volume. So the volume is 1 with respect to this volume measure here. So we let a point in the upper half plane be z equals x plus iy. Then the measure on this space is 3 over pi times 1 over y squared times dx dy. And with this measure, this space has volume 1. Okay, so what does the spectral decomposition look like in this space? So because it's not compact, it means that the Laplacian, spectrum Laplacian is no longer discrete. So we can write this spectral decomposition explicitly in the following way. If you have any nice function f, it can be written in terms of this expansion here. First off, we have the constant eigenfunction 1. Next, we have the discrete spectrum, the non-constant discrete spectrum. So these are Laplacian eigenfunctions. Obviously, we want to choose an orthogonal basis. So these are non-constant Laplacian eigenfunctions. And you can choose this basis to be something that's known as Hecker eigenfunctions. So there are additional operators acting on the space that commute with Laplacians. I will not talk about them at all. All I'll point out is that on this space, the discrete spectrum is actually conjectured to be simple. So this Hecker condition should be completely irrelevant because these eigenvalues should occur with multiplicity 1. So these are the Laplacian eigenfunctions. We call them Hecker-Mass cusp forms if we're a number theorist. For an analyst, you just call them non-constant Laplacian eigenfunctions. So it turns out these are quite complicated number-theoretically and have some really interesting properties. The continuous spectrum is parameterized by a continuous parameter t, such that the eigenvalue, the Laplacian eigenvalue is a quarter plus t squared. So these are known as Eisenstein series. If you're an analyst, you just think of these as generalized eigenfunctions. So these are not in L2, unfortunately, because the space is non-compact. It turns out that the L2 norm basically diverges logarithmically up the cusp. So they're very close to being in L2, but they fail by a logarithm. So they're parameterized, but yes, question?
Eisenstein series of weight too.
No, these are real analytic Eisenstein series. So the weight 0.
All right, they're functions. That's okay.
Yeah. So they're parameterized by t. They're continuously parameterized. And the inner product is here, where this is the volume measure. So this is the L2 spectral expansion in terms of Laplacian eigenfunctions. In this case, we have this remarkable result, essentially due to Lind and Strauss, which says that QUE is true. So QUE holds. If we take a Hecker-Mass cusp form, so a Laplacian eigenfunction that is additionally an eigenfunction of these Hecker operators that I don't want to talk about. If we take any sequence of these Laplacian eigenfunctions, then the L2 mass of these Laplacian eigenfunctions equidistributes on this manifold. So you can either think of this in terms of nice sets B, or you can also do this in terms of integration against nice functions F. Here we need to make sure these functions F are not just continuous, but they're also bounded because we're in a non-compact space. So I've written the eigenvalue of this Laplacian eigenvalue as a quarter plus tj squared. So here you should think of tj as being the square root of the Laplacian eigenvalue. I know if you're an analyst, you don't understand why there's a quarter here, but it turns out to be nice if you're a number theorist. Of course, I'm only interested in the high energy limit, so it turns out the quarter is ultimately irrelevant. It's just a kind of a nice normalizing factor. So this is the case for Laplacian eigenfunctions. And the same is also true for generalized eigenfunctions, for the continuous spectrum, so long as you normalize appropriately. So first off, we need to normalize by 1 over the logarithm of the eigenvalue. So we need to divide through the left-hand side by the logarithm of the eigenvalue. And we also need to restrict to compact sets because the L2 mass of this blows up logarithmically at the cusp. So we need to restrict to compact sets. Or equivalently, we restrict to compactly supported test functions. So the result for Laplacian eigenfunctions due to Lind and Strauss, and which is essentially what he won the Fields Medal for in 2010. For Laplacian, for Eisenstein series, for generalized eigenfunctions, it's due to Luo and Sonak a decade earlier. I should point out that Lind and Strauss's result is not just QUE in configuration space, it's QUE in phase space, so it's for the microlocal widths. This result of Luo and Sonak is only on configuration space, but it was generalized to phase space by Dimon Jacobson in his thesis. Although I did read the paper last night and I found out that there's a very minor gap in Dima's paper. Sorry, Dima, I'll tell you how to fix it afterwards.
Not to be bad, but Lind and Strauss's result is for the compact case, so Shimura occurs, right?
Yeah, so Lind and Strauss proved this on the compact case, and he also proved this on a non-compact case up to the possibility that there could be some escape of mass. So he showed that any possible limit of this sequence is a scalar multiple of the volume measure, but that the scalar could be a little bit smaller than 1. So you could lose mass possibly. And what Soundararajan showed a few years later is that this escape of mass couldn't happen. So obviously in the compact case, and you kind of escape of mass. The non-compact case, you could have escape of mass, and Soundararajan eliminated this possibility. Okay, so how do you prove this? So the proof I'm going to sketch is not how Lindenstrauss proves it. He proves it by ergodic methods, which I don't fully understand. I'm going to talk about how you might prove this by analytic methods. So the version of equidistribution I want to talk about is the version in terms of continuous functions. You look at the L2 integral of your Laplacian eigenfunction against a test function, and this should converge the integral of that test function. And by the spectral decomposition on L2 of your manifold, you only need to prove this for nice test functions. So you only need to prove this when your test function is itself a Laplacian eigenfunction, so either, or a linear combination thereof. So either a linear combination of the constant function or of these Laplacian eigenfunctions corresponding to the discrete spectrum, or direct integrals of the continuous spectrums, the Eisenstein series. So in this way, you reduce QE, showing that that for every nice Hagemas cusp form, for every Laplacian eigenfunction from the discrete spectrum, phi j squared integrated against psi, so this inner product here, which we think of as a triple product, converges to 0 because the integral of phi against the constant function is 1. And also for every fixed t here, this inner product also converges to 0 as tj tends to infinity. So you're fixing your test function psi, or you're fixing your Eisenstein series, and you're setting the Laplacian eigenvalue of this off to infinity. This is if phi j is a Laplacian eigenfunction in the discrete spectrum. If it's in the continuous spectrum, then things are a little bit difficult because this integral here does not converge, so you need to somehow regularize this, but this can be done. So all of this made sense up until now if M were not arithmetic. All of this strategy would have been completely valid if M is not arithmetic, but then you'd get stuck. And here's how you get unstuck in the case of the arithmetic setting. There's a remarkable result due to Watson and Ichino, which shows that this integral of phi j squared against another Laplacian eigenfunction psi can be decomposed, can be written as a product of something completely arithmetic and something completely spectral. So I'll tell you what these are in a second. And a similar thing holds if either of these are an Eisenstein series, if either of these are generalized eigenfunctions. So what this does is it turns out, it tells us that this triple product, which we want to converge to 0 as Laplacian eigenvalue of phi j tends to 0, tends to infinity. It turns out we just need to understand this arithmetic part and the spectral part. And what we can show is that the spectral part is very well understood. It only depends on the Laplacian eigenvalues of phi j and psi. And the arithmetic part is kind of complicated and depends in terms of these Hecker eigenfunctions. So because we're assuming these to be Hecker eigenfunctions of the Heck operators as well. This arithmetic part is kind of completely number-theoretic. Spectral part is completely spectral. This is really easy to understand. This is quite complicated to understand, but you might hope you can say something about this in this arithmetic setting. So the proof of this is by representation theory and relies on the fact that there's an arithmetic structure here and that the upper half plane is a symmetric space. So let me first tell you what the spectral part looks like. So you want to understand the spectral part in order to understand how we might show that this triple product tends to 0. It turns out the spectral part can be written completely in terms of products of the gamma function, of various values of the gamma function. And if we use Stirling's formula, then we can write it in the following form. So the absolute value of the spectral part can be written in the following way. So here, T psi, remember, is roughly square root of the eigenvalue of psi. So there's this kind of polynomial decay in T psi. There's this interrelation between Tj and T psi that is large when either one of these is large unless they're close together. And there's also possibly exponential decay if the square root of the Laplacian eigenvalue of psi is bigger than twice the square root of the Laplacian eigenvalue of phi j. So what this means is the following, is that there's polynomial decay of the spectral part if psi oscillates at some rate that's slower than the oscillation of phi j squared. There's some constructive interference if psi oscillates at the same rate as phi j squared. So this is this constructive interference here. This thing here is usually quite large, but it can become smaller if these are close. So if T psi is close to Tj. So you can think of this as constructive oscillation, constructive interference. Laplacian eigenfunctions, you can think of these as random waves that oscillate at some rate. And if these oscillate at similar rates, then you have this, they might have some really interesting constructive interference where you get large values from this. And finally, if psi oscillates more quickly than phi j squared, then all of a sudden this spectral part has very quick decay, it has exponential decay. So this is completely understood, but the arithmetic part is a bit more complicated. And I don't want to say too much about it, other than that it's related to L functions. So if you're a number theorist, you understand what these are. If you're not a number theorist, these L functions are generalizations of the Riemann-Zeta function. So the Riemann-Zeta function is just this thing here in terms of products over primes. And it's kind of the analytic continuation to s equals a half of certain L functions associated to these Laplacian eigenfunctions. So it has some product in terms of primes. So ostensibly, this shouldn't involve the spectral parameters at all, the Laplacian eigenfunctions at all, except because it involves the Laplacian eigenfunctions, there is some sort of dependence, but hopefully it's very minor. So because we understand the spectral part, we just need to understand the arithmetic part to say something. So if we combine the Watson-Ichino formula with asymptotics for the spectral part, you can say the following. Quantum unique ergodicity for the modular surface with this effective rate follows by understanding this L function here, by bounding this L function in terms of Laplacian eigenvalue, or the square of Laplacian eigenvalue, as Tj tends to infinity. So we just want this L function to be a little bit smaller than Tj. An optimal rate for this would be by showing that this is no larger than Tj to the epsilon, as Tj tends to infinity. And it turns out this is optimal. We can't replace Tj to the epsilon with 1. So this kind of confirms that this square root cancellation here is the best we can really hope for, because we know that we can't do better for this L function here. We know we can't bound this by something smaller. Unfortunately, the best we know for this L function, the best bound we know for this L function as Tj tends to infinity is just that it's no bigger than Tj. Whereas quantum unique ergodicity follows by showing that there's a little bit of a power savings. So this is known as improving this would be something known as subconvexity. Unfortunately, it's going to get unknown in this generality. And there is a conjecture, a completely number-theoretic conjecture, which says that, well, this L function really should be quite small. It should be no larger than Tj to the epsilon. So this turns out to be a consequence of the Riemann hypothesis. So we certainly believe the Riemann hypothesis is true, so we should certainly hope that this is true. And if it's true, it's optimal, we can't do better. So this tells us that we get quantum unique ergodicity with an optimal rate if we assume the Riemann hypothesis, or if we assume the slightly weakening integrator known as the generalized Lindelof hypothesis, which we call GLH. So I want to talk about in the last 10 minutes, or 5 minutes, is about small scale equidistribution. So we'll look at these Laplacian eigenfunctions here. And what I want to do is look at this shrinking target problem where I shrink the set, my target. So I'm looking at shrinking balls and looking at the mass in shrinking balls. So particularly we see that if that there are kind of sets that are quite small, so this little ball here, the Laplacian eigenfunction is very large, and so we shouldn't expect it to behave randomly. This is kind of the scale of the Laplacian eigenvalue. It's of the Laplacian eigenfunction. It's one of the square root of the eigenvalue. So the conjecture is the following, that the L2 mass of these Laplacian eigenfunctions equidistributes on these shrinking targets, so these shrinking balls with a fixed center, as the eigenvalue tends to infinity, provided that the radius of this ball is larger than 1 over the square root of the eigenvalue. And it turns out this is really the best we can hope for, because I can show that there is a countable dense collection of points for which, such that if you give me one of these points, then there exists a subsequence of Laplacian eigenfunctions for which quantum unique ergodicity fails on balls whose radius is within a logarithmic window of the Planck scale. So this does not converge to 1 as Laplacian eigenvalue tends to converge. So this is a failure of the QUE at the Planck scale. And Dima basically gave away the proof. He understands exactly what's going on there. On the other hand, we can make some partial progress towards small scale QUE. So if you assume the generalized limit hypothesis, if you assume the Riemann hypothesis, then for any sequence of Laplacian eigenfunctions, QUE does hold in balls set in the fixed point W, whose radius shrinks at some rate, unfortunately not all the way down to the Planck scale, but 1/3 of the exponent. So, whose radius is larger than Tj to the -1/3. So this is a result of Matt Young from 4 years ago. And what I showed in my thesis is that if we excise a bad set of centers of these balls, then we do get Planck scale mass equidistribution. So for almost every ball whose radius shrinks at an optimal rate, so any rate larger than the Planck scale, then we do have QUE. So you can think of this as excising a bad set of balls, excising a bad set of centers of balls, and getting optimal small scale equidistribution in every other ball. Those were both conditional on the generalized Lindelof hypothesis, and they were for Laplacian eigenfunctions. If we work with generalized eigenfunctions, these Eisenstein series, then again we get some unconditional result for each fixed center down to some scale, but far shy of the optimal scale. And if we throw away some bad centers, then we do get the optimal scale for these generalized eigenfunctions. And what Rizwan Khan and I were also able to show recently is that there is a thin subsequence of genuine Laplacian eigenfunctions. So these are L2, they're known as dihedral mass forms. For this thin subsequence, we do get QUE in almost every shrinking ball whose radius shrinks at the optimal rate. Okay, so that's small scale QUE. I'll also mention some progress that is known towards this Gaussian moments conjecture. So at the moment, this conjecture says that the nth moment of a Laplacian eigenfunction should converge to the nth moment of a Gaussian random variable. So for 0, 1, or 2, this is trivial. Turns out for n equals 3 in the arithmetic setting, this is known. And for n equals 4, this is quite hard. So the conjecture is that this moment, the L4 norm, the fourth power of the L4 norm, should converge to 3. So this is really quite strong. And there's a beautiful recent result of Jat Bakhain and Rizwan Khan that shows that this conjecture is true under the assumption of the generalized Lindelof hypothesis. Another recent result of Goran Jankovic and Rizwan Khan that shows that for generalized eigenfunctions, there's a version of this conjecture that's true. You have to kind of regularize this integral because it diverges at the cusp. And another recent result of Rizwan Khan and I, where we show that this conjecture is true unconditionally for a thin subsequence of Laplacian eigenfunctions known as dihedral forms. And these are genuine Laplacian eigenfunctions, they're in L2. So I'm kind of out of time, so I will try and say a little bit about the proof. I may go a few minutes over. Feel free to leave if I go on for too long. And feel free to cut me off if I'm taking too long. But I just want to sketch this kind of quickly. The idea is to think about this proof in the following way. We want to show that this quantity here converges to this. And you can think of this quantity on the left as being the inner product of phi j squared with the normalized indicator function of the ball of radius r centered at W. So because this is an inner product of two functions, we can spectrally expand it. We can spectrally expand this in terms of an orthonormal basis of Laplacian eigenfunctions and also the continuous spectrum. And if we do this, then we get a contribution from the constant function in our spectral expansion. This gives us the main term. Then we get a contribution from the discrete spectrum in this following form, and a contribution from the continuous spectrum in the following form. And because we know the answer should be the contribution from the constant function, what we need to show is that these terms, the contribution from the non-constant discrete spectrum and the contribution from the continuous spectrum converge to 0. So what we need to understand is this thing here, which we more or less do by this Watson-Ichino formula. We need to understand the inner product of a Laplacian eigenfunction with this normalized indicator function of a ball. So if you can think about this in this terms. So you have a Laplacian eigenfunction integrated over a ball divided by the volume of the ball. So if instead of Laplacian eigenfunction, this were a genuinely harmonic function, then this would just be equal to the value of psi at the center of the ball. This is the mean value property. And it turns out that in this arithmetic setting, something similar is true, which is that if you, basically, you have this heuristic here. If you look at the integral of Laplacian eigenfunctions over balls that are larger, whose radius is larger than 1 over the square root of the eigenvalue, so larger than the Planck scale, then you essentially have a mean value property. Basically, this is equal to psi of w times something that is essentially 1. So long as the Laplacian eigenvalue is smaller than 1 over the radius. Once you look at smaller balls, you get a large amount of cancellation, and this integral is very small. So this is true essentially for any symmetric space. So what we do is we plug in this asymptotic for this, this property here into this spectral expansion. And we get this expression here. Now we need to show that this tends to 0. And the proof of small scale QE works in the following form. Well, we understand how big these are by the Watson-Ichino formula. We understand the size of this by the previous slide, which basically means that this sum, instead of being infinite, is supported only on Laplacian eigenfunctions whose eigenvalue is less than 1 over the radius of the ball. And then we just bound this essentially by inputting these bounds and using the Weyl law. And if we do this, then we find that via these bounds, these quantities are smaller than, well, they tend to 0, provided the radius is bigger than tj to the minus 1/3. And all I've done is just taken absolute values and started bounding each of these things individually and used the Weyl law. And the reason why we don't get the optimal scale is that we're kind of missing out on some cancellation, because these terms aren't necessarily positive. They may have some kind of oscillation that we're missing out on. So we're not able to use additional cancellation. On the other hand, if you want to show small scale QUE almost everywhere, then it turns out that this is equivalent to bounding this variance. We look at the integral of phi j squared over a ball divided by the volume of the ball, subtract off the expected main term, we square, and we integrate over the centers of the ball. And again, we look at the spectral expansion of this. And now the spectral expansion involves the non-constant Laplacian eigenfunctions and the continuous spectrum. But now everything inside is non-negative. So when we try and bound this, we're not going to miss out on any cancellation. So if I do this, well, again, I put in the Watson-Ichino formula. And it turns out that due to this kind of constructive interference only kicking in when tj is near t psi, and because this HR function supports our sum only when tj is smaller than 1 over the radius, what this means is that if the radius isn't too small, well, then this is always small, and this is always small. One of these two is always small, and so this sum is always small. Whereas if the radius is too small, then this might be big, and this might also be big at the same time due to this constructive interference. So what this means is that if the radius is bigger than Planck scale, then all these terms are small, and we get this variance tending to 0, which means we get Equidistribution down to the optimal scale. And finally, for the fourth moment, we do the same thing. We do the same sexual expansion, and we get 1 from the constant term plus this thing here, where now we're no longer weighting by this h of r term. And remember that the conjecture is that this should converge to 3. So we need to show that these two terms contribute 2. It's exactly what it's 2. Now, if we just use Stirling's formula and Lindelof and the Weyl law and all these things, we can show that this is no larger than tj to the epsilon, but it turns out we need to work a little bit harder to get an asymptotic. So you can kind of need to treat this range of constructive interference with a little bit more care to extract this constant term 2 plus a small error term. And this really heavily uses arithmetic properties. I'll skip over this slide here and this slide here. And what I want to say is that when we prove things unconditionally, we're really using a lot of arithmetic input. We're really using deep subconvexity results. We're using a lot of really heavy arithmetic tools to get this result. I can say more later on if people have questions. And I'll end with this question that I'm kind of interested in, which is the fact that I'm using arithmetic properties here doesn't mean that we can't still ask this question in non-arithmetic settings. So if we have a non-arithmetic surface, if M does not come from arithmetic, we can still ask the following question. does equidistribution fail below the Planck scale? Do these Laplacian eigenfunctions have some non-random behavior below the Planck scale? And I think this should be provable by modern methods on non-arithmetic surfaces. But I am not a macro-level analyst, so I don't really have the tools, but I'll be interested if anyone can prove anything about this. Okay, I'll stop there, and apologies for going over time.
Thank you very much, Peter, for the very nice talk. So now is time for questions. If some
ask a question.
questions. Go ahead.
Igor, yes. Go ahead.
So in your logarithmic scaling,
Yes.
So you have a power A. Is the statement that it's for every A, or does there exist an A?
You'll be quite interested in this, because in the case that Igor has worked on the tori, there is a very specific kind of phenomenon where you have a failure at some logarithmic scale and you have a success at a different logarithmic scale.
Yes.
In the case of this arithmetic case, in fact, I get something even worse than this. It in fact turns out to be, the correct answer here is exponential of the square root of log over log log, something like that. So it's not actually log.
The statement is in fact, sorry, so I didn't quite understand the answer.
Every A is the answer to your question. Yeah, and in fact, something stronger than every A. There's a strength. Yeah,
got it.
So it's not just within a logarithmic window, but it's a faster growing function than logarithmic.
Yeah,
but
so there's
more
no
slowly. Yeah, so
there's no phase transition.
There may be a phase transition that you can climb, but not logarithmic. It's related to large values of L functions.
Yeah, okay, you spotted it right away why I'm asking that.
Yeah. It's a very interesting that in the case of tori, there's this really interesting transition which you can completely quantify, and here, unfortunately, it's not quite as nice. All right, so there's a question in the chat that I missed from Philippe Charon, which says, is there a way to approximate your indicator function on the ball of radius r with smooth functions that apply the eigenfunction or expansion? Yes, there is. And in this case, it doesn't really make much of a difference because although this h of r function only has this rate of decay, which is not quite nice enough, the other things here have exponential decay once you're sufficiently large. So this does converge absolutely. Usually you want to approximate your indicator function, smooth the function, because you're worried about issues when you spectrally expand or things like this, where things won't converge, because usually sharp cutoffs are bad. But thankfully, the slow decay of this from the sharp cutoff is mitigated by the exponential decay of this thing here. So it does not make a difference.
Peter, there's also a question from Semyon Dyatlov, who has raised his hand.
Hi, so I have a question about the last slide, the conjecture. Could you please quantify a little bit by what you mean by failure of ergodicity below the Planck scale? I'll clarify.
So what I mean, oh yeah, please do.
There is a kind of a trivial argument, which is probably not what you're looking for, is that, well, the eigenfunction has to be considerably larger than zero somewhere because it's L2 normalized, and then because it's oscillating at a scale above the Planck scale, then near that point it has, has to have some kind of, there might be kind of just basic arguments based on that, but it's probably not what you're looking for.
It's not what I'm looking for. So I think there is, like a 2-page paper you could write about this saying something, which is basically what you're arguing there. Basically, because these functions are non-constant, they behave in some way that you have to, you can't have Equidistribution down past the Planck scale. And then you might want some sort of refinement, which is what I wrote earlier. And I don't know if you can prove that in just in a general setting. I don't know if you need something. But I do agree there should be some sort of very cheap argument, which I haven't thought about to prove this statement. I mentioned this to Andrew Haskell when I was visiting in Australia, and he sketched out something, and he didn't go further, but he thought it might be quite cheap, as you mentioned.
But you should be careful with sign of n times x, right? I mean, because this guy is everywhere less than 1. So you should, you should make sure that you don't have a situation like that.
Yeah, I think that's correct. So the way I prove the failure at the Planck scale is this statement here is I'm showing not only does this not converge to 1, but it's much larger than 1. Whereas, you know, if you had something like sin x, it's smaller than 1, so it's hard to say something.
There are some in some paper there are some results by Fezin Nazarov that prove that on a very small scale you get counterexamples to, I think, to something else. To there are some other conjectures that the plus and minus parts of eigenfunctions are very much balanced. And which also, you know, is true for random Fourier series. So if you want, you can include it into the random wave conjecture.
Yeah.
And, but I think he had some fairly clever construction using complex variables, which says that on a very, very small scale, if you shrink the ball too fast, then this balance fails on the round sphere for some very specific spherical harmonics. And so maybe that would be also an interesting thing to look at. But and well, I guess just two small remarks. If you look at infinite volume hyperbolic manifolds, then there is a nice paper by my former student Patrick Monroe, who computed the moments of Eisenstein series in infinite volume if the Hausdorff dimension of the limit set was fairly small. So that's like 2016 in IMRM. And for, I guess, for Loschmidt-Echo, we did some related work looking at moments with so John Toft, Isaac Kanzani.
Yeah, I should mention that this whether state the moment conjecture. This Gaussian moments conjecture is actually false in the arithmetic setting once you take n to be large, like say larger than 12, just because of the fact that it's not compact. It has finite volume, but it's not compact. And it turns out that even though you have QEs, there isn't escape of mass at the cusp. There are kind of unusually large values of these Laplacian eigenfunctions in some sense occurring near the cusp. So when you take high moments, this actually can be unusually large in the non-compact setting.
There was also a raised hand by Grigory Berkolaiko. If you have a question, Grigory, go ahead.
Yeah, thank you. My question is, what's the analog of Ichino-Watson formula for non-arithmetic setting? Like the arithmetic part is kind of seems like lengths of geodesics and spectral is spectral, but is there something?
So I think it's kind of hopeless to say anything useful about it in a non-arithmetic setting. I think it really uses quite heavily the fact that it's arithmetic. So I think if you're in a symmetric space, which is not necessarily arithmetic, then you can still say something about this spectral part, and you can do something here. There's this work of Reznikov understanding this. But I think the arithmetic part, all you can do is, you can't explicitly describe it in a useful way. And I don't know how you would, you can conjecture that it's small because we have this random wave model that would say it's small, but I don't understand how you would explain in terms of lengths of geodetics or length spectrum or anything like this. I think it truly is kind of only understood in any way in arithmetic settings, unfortunately.
Thank you.
Can it be true if you take, spherical harmonics that are eigenfunctions of Hecke operators in the sphere?
Yeah, I keep getting around to writing a paper about this at some point, but I've been too lazy. But yes, this is another form. This is another form of Ichino's formula. If you look at Hecke eigenfunctions, so you look at Laplacian eigenfunctions in the sphere, then you have very high multiplicity of eigenvalues. And it turns out you can choose a basis of these, which are eigenfunctions of Hecke operators. There are Hecke operators in the sphere, just as there are Hecke operators on the modular surface. So you can kind of choose a particular orthonormal basis, which these are Hecke eigenfunctions. And then it turns out that there is this kind of formula still holds.